Hello and welcome back to ML with Phil. This video is part 2 of our previous video entitled RNNs tutorial number 3, translating sentences using an encoder decoder with cross attention. So in the previous video we built the encoder decoder architecture and we took the final hidden state from our encoder and used that as the initial hidden state of our decoder, and that's how we passed along the information from the encoder to the decoder. However, that is not the best way to pass along information from our encoder into our decoder. It's not the best way to encapsulate all of the information from a French sentence and use it when we try and build up our English sentence output. So what we're going to do in this video is we're going to actually implement the cross attention part of this into our encoder decoder. Now, attention is a very powerful and important mechanism that is used in things like GPT models, for example, ChatGPT. In this video, I'm going to explain how attention works and how attention essentially, as is stated in the name, allows us to pay attention and learn which things to actually pay attention to that are important for making the next prediction. So we allow the neural network to learn how to pick out the things that are important and that are relevant to the current piece of information that we have. This video is adapted from the PyTorch tutorial called Translation with a Sequence-to-Sequence Network and Attention, authored by Sean Robertson, and I will link that in the description for you to take a look if you're interested. I do change quite a lot of things in this video. Instead of using BADA now attention, I opt instead to use scaled dot product attention. If you're interested, I suggest taking a look at that tutorial. It's a very great tutorial and it inspired this video. In addition to that, I would also recommend the YouTube video by Andrei Karpathy called Let's Build GPT. We actually take all of the code for the attention mechanism from that video, and there's a great explanation of how attention works there, so I encourage you to take a look at that video as well. Now, without further ado, let's get started. What I want to start with is drawing out a diagram of how cross attention is going to be implemented for our specific use case, so that you can get some intuition behind how it works and how we're going to implement it into our architecture. All right, so as mentioned in the intro to this video, I recommend you take a look at Andrei Karpathy's YouTube video, which I will link in the description, for a very good explanation and visualization of how attention works. But I will try and demonstrate how we're going to implement it for ourselves and use cross attention between our encoder and our decoder. So if you recall, we have an encoder, okay, and the encoder is going to process our French language sentence. So the sentence that we're going to process is J'aime les chiens. Okay, and our decoder is going to build up our English language output. So it's going to be responsible for trying to generate the sentence, I love dogs. Okay, and we have time steps. So this is going to be t equals 0. We'll call this x0, x1, x2, and x3. Similarly, this is going to be x0, x1, and x2. Okay, and so at each time step, we're going to take in a hidden state, h0, take in the input x0, and then we're going to produce the output y, we'll call it y0, and h1, and so on. And then we produce y1, and we produce y2, and produce y3. Okay, and then we produce some hidden state at the end. We'll call this the encoder hidden state. And what do we do in the decoder? Similar process. We take an x0, we take an initial hidden state. So we're actually going to take in the hidden state from the encoder, and we're going to produce a prediction, and we're going to produce a hidden state, and we're going to produce another prediction, and we're going to produce another hidden state, and so on and so forth, right? What we currently have is the only information that we're getting from the encoder, the only information that we're getting from the French sentence is we're just getting this final hidden state, HE. And that's going to be used in the decoder when we try to generate our English sentence. And we want to improve this. So we're going to implement what is called attention. And how attention works is it has a set of keys and it has a set of queries. So the query is essentially what you're looking for. Think of it like when you're making a search. The query encodes the information that you're trying to find. And the keys, well, the keys are all of the things that you're searching through. So all of the potential candidates that you're trying to pick from. And you can think of the key as essentially encoding the information that is contained within each of those items that you're looking through. And so when your queries and your keys are very similar, when they match up, that's when they have a large attention weight between them. What this looks like for us is our keys, so the things that we're going to be looking through are actually going to be our encoder outputs. So our keys are going to be Y0, they're going to be Y1, going to be Y2 and Y3. These are the keys. Okay, and let's just give them some random values. And here we have H0, here we have H1, and here we have H2. Okay, so let's give this a value of 10 and 1. Let's give this a value of 1 and 10. Let's give this a value of 4 and 4. And let's give this a value of 2 and 1. Okay. These are just some random values that I came up with. Okay, and what happens to our keys is they go through a linear layer and they actually get transformed, encoded to a new set of values. But let's say these were the final values of our keys after the encoding. Okay, cool. And then the keys are the things that we're searching through. And the query is the things that we're searching for. So for example, in our queries are going to be our hidden states. So H0, H1, and H2. So our hidden states have all of the information about all of the previous words that we have generated in our English sentence output. And so the hidden state, when it goes through the query linear layer, it's going to encode what we're actually trying to find, what is relevant to what we're looking for. So let's just go ahead and do this. We'll say H0 is 10 and 1. So at the first time step, what we're going to do is we're going to take a look at our query, which is H0. So these are our queries. Okay, and our attention is defined as the queries dot product with the keys, which is equivalent to doing a matrix multiplication of the Q and the keys transpose. So this is what our attention weights are equal to. Okay. Now keep in mind that when the query and the keys align very well, we're going to have a much higher attention. So let's do this here. So our Q is 10, 1, 4, 2, 1, 10, 4, 1. And our K transpose is just going to be 10 and 1. And what do we get when we do that multiplication? Well, we're going to get a four-dimensional, we're going to get a matrix with 4 values. So the first one is going to be 10 times 10, which is 100, plus 10 times 1, which is 10. Okay, and then 10 times 1, which is 10, plus 1 times 10, which is also 10. 10 times 4, which is 40, plus 10 times 1, which is 4. 10 times 2, which is 20, plus 1 times 1, which is 1. So we're going to get this. Yeah, so 110, 20, 44, 21. And these are our attention weights. So this is W1, W2, W3, W4. Okay, and you can think of the attention weights as basically how much attention we're going to pay to each one of these keys. So this means that we're going to pay the most attention to the first key, which roughly corresponds to the first letters in the first word in the encoder, je. So we care most about the word je when we're trying to predict our first English word I, which, that makes sense, right? Because we want to find the French word that corresponds to the current English word that we're looking for. Okay, and you can think of attention as essentially a weighted average, where the weight of each of the things that we're averaging is going to be equal to their attention value. So these are the weights that we have. And now what we're going to do is we're going to normalize these. So we're going to pass them through a softmax. And this is going to ensure that all of the weights are going to add up to 1. Okay, now if we were to take the softmax of these, we would end up getting extremely, extremely small numbers, because these are huge exponents to take e to the exponent of 2. So we're actually going to scale this down and divide everything by 100. So let's pretend that our values actually ended up being 1.1, 0.2, 0.44, and 0.21. This wouldn't change anything. I'm just pretend we divided everything by 100. Okay. So now our softmax values are 0.43, 0.17, 0.22, and 0.18. Now these represent the weights, how much attention we're going to pay to each of these. And in our case, our values are just going to be our keys. So for our case, our values are equal to our keys. So these are our keys, and they're also our values. So we're basically going to take a weighted average of these values. All right, so now that we have our attention weights, all that's left to do is to calculate the actual attention scores, or the context, which are the values that are going to get outputted from our attention mechanism and are going to be used in the GRU in order to predict the next English word. So all we need to do, as I had mentioned, is that attention is simply a weighted sum. And we've calculated our weights here, and our values are simply the keys that we used before. So all we need to do to get our attention scores is we need to take our weights and we need to do a matrix multiplication with our values. And that will do the same thing as taking a weighted average of the values with our weights. So these are our values. Our values are the matrix that we had before. I'm just going to flip the matrix because we should have actually had it. We should have had the rows and the columns in the opposite order. So I'm just going to do that here. So this is our value matrix here. So we have 10, 1, 1, 10, 4, 4, and 2, 1. This is V. And we want to just take each of these values for all of the different keys at each time step, and we want to take a weighted average according to the weights that we calculated. So all we need to do is we need to take our weights, which I'm going to again flip them to, because we should have had the rows and the columns switched in the first place. So these are our weights. So 4.47, 1.87. I'm just going to move things over to make some more room here. All right, so we have 4.47, 1.87, 1.76, and 0.54. Okay, so when we multiply these two together, okay, I just shifted things over for better visibility, but we're just going to do the matrix multiplication for these. Okay, so when we do this matrix multiplication, this is what we're going to get. We're going to get 10 times 1.47 plus 1 times 1.87 plus, you can kind of fill in the blanks. And then you have 1 times 4.47 plus 10 times 1.87 and so forth. So we're literally just taking a weighted average of these two columns using our weights as the weights. And we do that along both of the dimensions, and then we're going to get a one-dimensional vector. We're going to get a one-dimensional vector that's going to have two columns. So when we actually calculate this out, we're going to get, so I just put it into a matrix multiplication calculator, but when we do this, we get the values, we get these values, okay? 54.69 and 30.75. So we get 54.69 and 30.75. And these are our attention scores. And we're going to repeat this 3 times. So we're going to repeat this for as many time steps as we have. So now this value of 54.69 and 30.75, it would go into the GRU over here. It would go into the GRU here. And it would be used to calculate the next prediction for the next word. And then we would calculate the next hidden state. And let's say the next hidden state was 5 and 5. Then we would repeat this whole process using the value of 5, 5 instead of 10, 1 here. And we would make the next calculation. And then whatever we got as an output, we would stack it with the output from H0. And we would essentially get a 3x2 matrix for each time step and for each dimension that we have in our feature space. So like I said, this is scaled dot product attention, and this is cross attention, which means that we're taking our keys and our values from our encoder and we're applying our attention weights to the encoder's values. But we could also do self-attention where we apply the attention mechanism to the words in the decoder. So you can apply attention to the previous words that we've already generated and seen in the decoder. But we're not going to get into that, but just wanted to mention it. So I hope that this diagram helped explain and make more real some of the math and the calculations that are going on here and what goes on behind the scenes in attention and how it looks like in practice. We're going to take everything that we've demonstrated here in this diagram and we're going to build it into our architecture in code. So I hope this diagram was useful to you. And I also recommend taking a look at the YouTube video from Andrei Karpathy that I have linked in the description. Without further ado, we can now move on to the coding. All right, so I hope you guys are excited because this is going to be a really cool video. We're going to implement attention. Attention is a super powerful technique that's used in all kinds of the most cutting edge neural networks. It's used in ChatGPT most notably. So it's really awesome to implement something like this, which is such an integral part of the most advanced neural networks. We're going to start with the sequence-to-sequence translation code that we had from the last video. Okay, and from here, all we're going to do is add on attention to our neural network. Now, before we do that, I just want to get some housekeeping stuff out of the way. I want to replace our encoder steps with optimizers. So that's just going to be a couple of lines of code. And what we're going to do is we're just going to define two optimizers. So we're going to define the SGD optimizer, which is stochastic gradient descent. And this corresponds to just taking our learning rate and multiplying it by the negative of the gradient, which is what we're doing here. So we're just going to do this in an optimizer instead of doing it ourselves. We're just going to let the optimizer do that. So that's all that I'm going to change. So these optimizers are essentially just going to do the forward step and modify the parameters the same way. I'm just doing this to make things a little bit cleaner. Okay, now with that out of the way, let's go on to implementing our attention mechanism. And the form of attention that we're going to be using is something that is called scaled dot product attention. We're going to define a class called scaled dot product attention. Okay, and it's going to require the hidden size. Okay, and it's going to have a forward method. Okay, so remember we mentioned in attention we have three values. We have our query, our keys, and our values. And our keys and our values are going to come from the same place. And our query is going to just be our hidden state. And our keys are going to be our encoder outputs. So our query is equal to the hidden state. And the keys are equal to the encoder outputs. Okay, so just stating that explicitly, we need to take the query and we need to pass it through a linear layer. So we have a linear layer for the query. We'll just call it query. And each of our linear layers are just going to have hidden size and hidden size. And self.keys is equal to nn.linear of hidden size, hidden size. Okay, so we're going to pass our query through the query linear layer. So this is going to be self.query of the query. K is going to be self.keys of K. Okay, and if you remember from our diagram, what we do after that is we do the dot product of Q and K. So we're going to get our weights are just going to be Q multiplied by K dot transpose. Okay, and we're going to transpose the first and the second. We're going to flip the dimensions. All right, simple enough. Then here's where the scaling part comes in. For scale dot product attention, we actually want to scale our weights by a scaling factor, which is just going to be 1 over the square root of our hidden size. Okay, and then we want to take a softmax. So I'm going to take a softmax over the first dimension. Okay, and then we are going to calculate our values. So self.values is equal to nn.linear of hidden size, comma hidden size. And we're also going to define the hidden size. Okay, so this is all straightforward. This is exactly what we did in our diagram. So self.values of the keys. And sorry, this should be keys as well. And then our context value, or our scores, is going to be equal to the weights matrix multiply the values. Okay, and then we are going to return the context and the weights. So we're going to import NN. Okay, so that looks fine. Our encoder doesn't change at all. Okay, our decoder now. So in our forward step, we're going to actually get the context and we're going to get the weights from self.attention, and we're going to pass in the hidden, and we're going to pass in the encoder output, and we're going to actually have to take in the encoder output in our decoder. We're going to concatenate our context, our output from our attention, and our input to give it a new input. So we're going to concatenate the input and the context together, and we're going to get a combined value. And then we're going to just pass in combined into the GRU. So now instead of just passing the input by itself, we're going to get context by calling the attention mechanism, and then we're going to use that, sorry, this is dimension equals 1, and then we're going to use that in our GRU to generate the output. And everything else should stay pretty much the same. So maybe let's just test this part out and make sure that the dimensions all match up. So let's copy this code, and we call the encoder. Okay, so let's encode everything, and then let's try and do a single step in our sequence. So if you recall, our query is equal to our hidden state, and our hidden state gets initialized to as our encoder hidden. So this is our query. Okay, and then the keys are just going to be the encoder outputs. So let's call this encoder outputs. So our keys are equal to our encoder outputs. Okay, instead of self.query, we'll just do, each of these linear layers are going to have the same dimension, so we'll call this lin is equal to nn.linear of hidden size. Okay, so we'll just explicitly define it to be 128, 128. Okay, so now what we will do is we'll pass each of these through the linear layer. Okay, and we should get everything stays the same shape as before, which it does. All right, now we should be able to take the dot product between Q and K by doing this line. Okay. And we should get 10 weights, which correspond to all of the 10 French words. And we do, which is good. And then we're just going to take the softmax of that. Okay, and we're going to want to import I want to import that. Okay, so these are our weights. Okay, and that looks good. Okay, and then we're going to do the same for our values. Okay, and the shape makes sense. And now we're going to take our weights and we're just going to matrix multiply them by our values. And that makes sense. Okay, so all of our shapes line up exactly how we want. So it looks like we've implemented things correctly here. So let's try and run this through the decoder and see what we get. Okay, sorry, we need to, of course, pass in the encoder outputs now. And we have to define attention, of course. So self.attention is equal to the scaled dot product attention. Okay, and we have to pass in the hidden size. Okay, now this should work. Okay, and for the GRU, since we've concatenated the input and the context from the attention, we're going to have to adjust our GRU to now have 2 times the hidden size. Sorry, 2 times the hidden size as the input. Okay, and that should work now. So let's run this. Okay, everything seemed to work. So now let's try and train our neural network and see what we get. And yeah, we have to make the same adjustments here. So we'll go encoder outputs, encoder hidden is equal to this, and we add our encoder outputs into our decoder. And now we try and train everything. Okay, so everything seems to be training as we expected. So now let's give that some time to finish running, and then we'll check back in and see what the results look like. All right, so taking a look at our results now, we noticed a slight improvement from what we had before we implemented attention, which is good, but we could do a lot better. The thing with attention is attention learns a lot better because it has all of these different parameters. It's much more complex than just a GRU. It actually works better when we give it larger batches to calculate the gradient. So what we're going to do is now we're going to implement batching into our neural network so that we, instead of passing just a single example each time, using that to calculate the gradient and do our forward step, we're going to pass a batch and process a batch of examples all at once. That'll give us a more accurate estimation and make the learning a lot more steady. So let's implement that now. Okay, so the first thing that we want to do when we're trying to implement batches. We're going to want to modify our way of passing examples through our neural network. So let's run everything from the top. Okay, so we're going to create a function called getBatch. We're going to create a function called getBatch, and what it's going to do is it's just going to return a batch of samples. So we're going to do a random sample of our pairs with the batch size. Let's start off with a batch size of 8. Okay, so we're going to get batch is equal to that. And then let's start off with our French sentence and encoding that. We're going to have to slightly modify the way that we encode our sentences. So right now we are just using this sentence to indices to encode a single sentence, but we're going to want to do that for multiple sentences. So our French sentences are just going to be the first index for each of the items in our batch. Okay, so these are our French sentences, and for each of our French sentences, we're going to want to encode them into a tensor. And we're going to want to add that to an array of tensors. So we'll call this French sentence still, and we'll call this sentence, and we'll call this our French tensor. The French tensor is going to have a shape of 10. So our French tensor is going to be, it's going to have a shape of our batch size, and then it's going to have a shape of our max length plus 1, and then it's going to be torch.long data type, and we're going to fill it with our start a sentence token. Okay, so this is our French tensor. Okay, it's just a bunch of zeros, and then we're going to iterate through all of these French sentences. We're going to convert them to a tensor, and then we're going to basically take the French tensor for I in range of batch size. Let's do it that way. French. Okay. We're going to do French tensor at I all the way up to let's just call the sentence. The length of the sentence okay. Alright, so we're basically just going to fill in all of the values in this placeholder array with all of the values of the French tensor, and then we're going to return the French tensor. Okay, so okay, so that looks good now, and okay, and our French tensor looks good as well, right? So this is the start of sentence token, these are all the words, and this is the end of sentence token as we want. Wonderful. And we would do the same for the English sentence. Let's put this piece into a function called encode sentences. And it's going to take in some sentences, and it's going to take in the language that we want. So our tensor is just going to be equal to this, and then sentence, the lang. Well, let's just do I in range of len of sentences. We'll do it that way, so that it can accept any batch size, whatever the batch size may be. And then we'll change this to tensor, we'll change this to sentences, and then we'll return the tensor. So let's try this now. Code sentences. Okay, looks like it works. Cool. So that's good. So then to get a batch in our get batch function, we're going to specify the batch size, and then we're going to go batch is equal to this, and we're going to go French sentences is equal to, okay, and then we're going to go French tensor is equal to encode sentences of French sentences French. And we're going to do the same thing for the English sentences. Okay. And we're going to do sentences. Okay. And we'll do this, and then we'll return the English. Sorry, we'll return the French and the English tensor. Okay. So let's do get batch of batch size. This should be lang. Okay. Okay. Now let's try it again. Okay, wonderful. So this looks correct. All right, so that's good. Now we've been able to get an example to pass through our neural network. What is going to change now? Well, for our French tensor was just a single entry. Now there's 8 of them. Okay, so now we want to just make sure that when we pass everything through our encoder, it all works out the same as before. So our embedding layer. So let's create an embedding and make sure that we get the same results. Okay. So we'll do nn.embedding. The input size is equal to eng.n_words, and the hidden size is equal to 128. And we'll call this on our French tensor. Sorry. Yeah. And now, perfect. Everything worked as we expected. And then for our GRU, everything will work. The only thing is the GRU knows how to process a batch. The only thing is we need to define our hidden state. Now, there's one important thing that you need to note here. If we look at the documentation for the PyTorch GRU, okay, you'll see that when we pass a batch first of true, this does not apply to hidden or cell states. So that means that the hidden state, the input is going to have the batch dimension first, and then it's going to have the sequence length, and then it's going to have, you know, the dimensionality of the vectors. It's actually going to be the opposite for the hidden state. The batch dimension and the sequence length are going to be flipped. So when we do it this way, normally we would have our batch dimension be first, which is just max length plus 1, and then we would have it like this. However, because in the GRU documentation this is reversed, we're going to have it this way. Okay, and then aside from that, everything I believe should be the same. So let's try and pass this into our encoder. And we got an error. Did we not read? Oh, sorry, we have to redefine this. So we're going to redefine this here, and now we're going to try it. And we expected a hidden size of 1.8.128, but got 1.11.128. Oh, sorry. Our hidden state has nothing to do with our sequence length. It's actually the batch size. So my mistake there. So yeah. So the sequence, it's always going to have 1 in the sequence length dimension because the hidden state is a single vector, and then we're going to have the batch size here. So this is actually what we want. So let's fix that. Oh, and we have to redefine it. Okay, so it seems like it worked. Let's check our shapes here. Okay, cool. So that looks like exactly what we want, right? We have 11 by 128, which is what we typically get, but now we have 8 of them for the 8 different items in our batch. Okay, now let's work on the decoder. So we no longer need this. All right, so this is going to be a doozy. So our input now is, well, we used to pad our input, but we've actually already padded our input beforehand, so we no longer need this. Because recall, our input already starts off with start of sentence tokens, filling everything, and then we put all of the values in. So we don't need this padded input anymore. So we no longer need this, and we no longer need the sequence length either. Yeah, we don't need any of this stuff anymore. We just need the encoder hidden, and yeah, we can just pass the input into the embedding, and then the output now, so it's going to have a max length of 1, but it's also going to have a batch dimension. So this is going to be equal to the batch size, which would essentially be the first dimension. So we'll go batch size is equal to the input dot size at 0. Okay. And then our outputs are going to have a size of batch size, the sequence length, and the hidden size. We're now going to go, now that we have an extra dimension, we're going to have to go all of the batches, then that time step, and then all of the vector dimensions. And then here we're going to go outputs at I is equal to maybe we'll do I to I plus 1 is equal to the output. Okay, so now we make sure we're slicing into the correct I. Okay, so that looks good. I think that's everything here. On the forward step, we're going to have to change some things, and we're going to have to change the attention mechanism quite a bit. So let's copy everything here and try and make sure that everything works out. So okay, so if you recall, our hidden state gets initialized to the encoder hidden, so we can have that as a starting point. Encoder outputs, they are just the encoder outputs. So these are encoder outputs, this is our hidden. Okay, so that part looks good. Our query is equal to the hidden state. Our keys are equal to encoder outputs. Len is equal to nn.linear 128, 128. We'll do this. Okay, so another thing actually that I just realized is our hidden state, the batch dimension is actually in the second place, while in our encoder output it's in the first place, and that's because of that. That's because of like how the GRU is set up. So we actually want to permute this to make sure that we have the correct dimensions. So we're going to go okay, so we just swapped the first two dimensions, and then now we should be good. So okay, so now the batch and the time dimensions line up. Okay, and we do this, and then we'll go q.shape. So this is correct. K.shape, this is also correct. Okay, and then we want to do q.product with k transpose. So what we can do is, well, we want to transpose these two dimensions. We don't want to touch the batch dimension. So k.transpose, specify the ones you want to swap. Okay. Okay, so that looks good. So k.transpose 2 and 1, and we want to multiply that q makers multiply with k.transpose. So we can go weights are equal to q at k.transpose, and then we can do this, and then now when we take the softmax, we want to take the softmax over the last dimension. So okay, that looks good. So let's take a look at index 0 and okay, so that's exactly what we want. All right, so weights is equal to f.softmax of weights at dimension 2. Okay, v is equal to len of keys. And then matrix multiply should also work as we expect. So context.shape. Okay, cool. Yeah, we have 8 and 128. So we just have an extra batch dimension on here, and everything else looks the same. Perfect. So that's all we need to do to change our attention mechanism to make sure that it works. So we need to permute the hidden. So let's merge all of this below. And make sure that that's what's in our attention mechanism. Okay, so don't need this. We do need this. Okay, so we do need to permute the hidden. We do need to permute the query. Don't need any of this. Okay, the weights we want to transpose with these dimensions. The softmax, we want a dimension of 2. And everything else is good. Okay. So now let's make sure that when we concatenate our context, everything works. These are our encoder outputs and our encoder hidden. And we can pass those into scale.product attention with the hidden size of 128. And we can pass the encoder outputs and the encoder hidden in here. And we can go context and weights is equal to this. Okay, so this is our context. We're going to have to concatenate this with the input. And the input is the English tensor. And we just pass it through an embedding. Okay, so this is going to be our input. Okay. Okay, so now we want to concatenate the input, but we want to take the input at a specific index, and we want to concat these together. So we want to do torch.cat of this and this. And which dimension do we want to concatenate it along? Well, we want to concatenate it along the last dimension. We want to concatenate the input and the context over the last dimension. And that gives us the shape that we want. Okay, so we can just make this dimension 2. And I think everything should work out. Okay, so let's give this a try now. And we got an error. Oh, we redefined the English tensor here. That is not good. Let's do this again. Okay, so now it worked. Perfect. All right. Whew. Looks so we've implemented batching now, so we can actually train our neural network in batches, which is pretty awesome. But we just need to slightly modify the loss calculation, because we now need to sum this loss over the total batches. But we're going to slightly change this. We're not going to use the targets. We're just going to use because we know the targets are just the English tensor with 1 until the end. We don't really care about the sequence length because we want to calculate the loss over the entire sequence. So I don't think we need that anymore. Yeah, we're going to move this all over, and we're going to go for I in range of batch size. And we're going to move the total loss over here, and we're going to have this be the batch underscore loss. So we're just going to go the max length for I, okay, we'll call this J. For J in range of the max length plus 1, we'll do the loss is equal to outputs and targets. I think we actually want to do max length. We're now skipping the last time step, so I don't think we need this anymore. But let's leave it in here and see if we get an error, which I'm pretty sure that we should. The batch loss plus equals to the loss. So now instead of having the sequence length, we're just going to have the max length, because every single one of them have the max length. I'm going to do total underscore loss divided by equal to the batch size. We need to take the outputs at that item in the batch, and then that time step. We want just the max length. Okay, cool. So let's make sure that everything is working. Loss equal to loss. and then batch loss is equal to batch loss, and then we'll print the total loss is equal to the total loss. All right, so we're getting the loss and the batch loss, and yeah, the batch loss is basically just the average, and then we get the total loss. Okay, great. So let's remove that now, and let's wrap this in a function called getBatchLoss. And what we need is the outputs and the targets. Okay. And we return the total loss. Okay. So let's make sure that this works. Get batch loss of the of the outputs and the targets. I may have gotten rid of this somewhere, or maybe I forgot to include this, but we want to also do total loss plus equals to batch loss. Okay. All right, great. So looks like that's working. So what we're going to do here now is we're going to just copy this code. Okay, so I'm going to fetch a random batch. I'm going to zero the gradient. We're going to do our encoder stuff. Okay, going to do our decoder stuff. Okay, and we're going to do our calculating the loss stuff. Looks okay. Let's try this out. Okay, so everything seems to be training as we wanted to. Hey guys, so before we start our training, there's a couple of small mistakes and adjustments that I want to make. And I only realized these after I started looking through the code myself while I wasn't recording the video. So let's go back and fix these because these are quite important. So the first mistake that we need to fix is we were taking the softmax over the first dimension. And now that we're using batches, we add an additional dimension. So our actual features and our hidden dimension is going to be in the second dimension. It's going to be our last dimension. So we want to actually adjust this to be dim is equal to 2. The other thing that we want to do is when we call our forward step, we should be passing in the encoder outputs here. So we should be passing the encoder outputs into our forward step, and that should be an argument over here as well. Okay, because we use our encoder outputs in the forward step, so we need that argument there. So those are the two mistakes that we needed to fix. Another adjustment that I wanted to make, because when I actually tried training this, I realized that it would take extremely long to train if we don't make this adjustment, is instead of just using the standard stochastic gradient descent, we're actually going to use a different type of gradient descent called Atom, which you probably have heard of if you're familiar with deep learning. So I'm going to make those two adjustments. Okay, so we now use Atom instead of stochastic gradient descent. Okay, with those two adjustments, I think we should be good. I'm also going to just adjust the batch size and the learning rate slightly. 0.001 and 32. Now let's try and train our neural network and see what we get. Okay, great. So this is working as we expected. Now, I don't want to let this train all the way because I want to make some adjustments that we're going to have to make to the actual neural network in order to be able to make predictions. If we want to predict, we would have to retrain the entire neural network from the beginning. So instead, I'm going to build that in now and retrain it again later. And another thing that we want to do before we go on to training is instead of training in this way, we want to use the more standard approach that you'll see in typical Torch neural network implementations of creating a Torch dataset. So let's do that now. And we can go here, create Torch dataset and sampler. Okay, so instead of just fetching, a random batch of examples like we're doing here, we're actually going to create a sampler and a data loader, which Torch is going to use automatically to sample data and to feed it into our neural network during training. And this is going to be a lot more efficient than what we're doing now. And it's going to ensure that we go through every example in the data set. We're going to define a tensor data set. And the tensor data set is just going to be all of our English and our French tensors. So what we're going to do is we're just going to encode the entire data set. So we can use our getBatch function, which encodes the data set with a random sample equivalent to the batch size. We can just modify this to be encode dataset, and instead of taking a batch, we can just take all of the pairs, and we don't need a batch anymore. So we can do this and this, and this should encode our dataset. Okay, so now we're going to encode all of the sentences. So we're gonna remove batch size. We're just gonna go the length of the sentences. Right, we don't need the batch size anymore. Okay. Okay, let's see here. So let's make sure this makes sense. So, okay, that looks good. Okay, taking a look at some of these, and this looks correct. Okay, wonderful. So now that we've encoded our entire French and English dataset, all we need to do is pass it into our tensor dataset class. Okay, wonderful. And then to create our sampler, okay, we just do random sampler of our data. And then to create our data loader, all we need to do is train_data loader is equal to data loader our train data, our sampler, and our batch size, which we will set to 32. Okay. Let's try this out. So the train data loader is going to be an iterator, and so we can get a single item out of the iterator by calling these functions on the data loader. So this should be our batch, and let's see what our batch looks like. So we should have a French tensor and an English tensor. We do, okay, so looks like that is exactly what we're getting. So maybe we'll put this first up here, and then this is where we are passing an example through our neural network. So here we create the data set. Here we're going to take a single batch from the data set, and then we are going to pass it through our neural network. Let's do and seems like it's working, so that's great. Now what we are going to do is we're going to modify our training loop here. Now we're not going to count iterations. We're actually going to, the sampler is going to sample all of the data from the entire data set in batches, and it's going to go through the entire data set. And when it goes through the entire data set, that is a single epoch. So we're going to train according to the number of epochs that we want. So we're going to go 80 epochs. We no longer need to keep track of this average loss, and we don't need this checkpoint because we're not keeping track of the iterations anymore. And now we're going to go and iterate through the number of epochs. And then for each epoch, we're going to set the epoch loss to 0. And we're going to print starting epoch. Okay, and now we're going to iterate through all of the batches that our data loader is going to give us. Okay, so we have the batch already. So this is our batch. Sorry, we should be setting the encoder optimizer and the decoder optimizer to have the 0 grad, but I don't think it makes any difference. Everything else should essentially stay the same, except instead of the average loss, we're going to keep track of the epoch loss. We're going to go the epoch loss plus equals to the batch loss. We're no longer going to, we're now just going to print every single iteration. Okay, our losses, we're now going to append the iteration and the epoch to our losses. So remove this, and we're going to print the epochs and the iterations. Okay, and we're going to go, our batch loss is equal to our batch loss, and we're going to append the epoch and the iteration and the batch loss. And okay, so for each epoch, we're going to do that. We're going to keep track of the loss of every single iteration, and we're also going to print the loss at every iteration. We are also going to normalize the epoch loss at the end by the length of the data loader. And we are going to append the epoch loss right at the end. Okay. And we're going to print the epoch loss oh, yes, I'm missing the end quotation. Okay, and I'm just going to print some separators as well, just to make things a little bit clearer. Okay, now let's give this a shot and see what we get. Okay, let's restart. Okay, great. Looks like our neural network is training successfully. So that's awesome. So we were able to speed up our training quite a bit by using Torch's data loaders. And now, instead of letting this train all the way to the end, because it is going to take quite a while, we actually do need to make an adjustment to our code in order to be able to make predictions on our data. Right now, when we're trying to make a prediction, we actually do not have any input in our decoder. So the way that our decoder works right now is we have an input, which we feed it, which is the true English sentence tensor that we're trying to predict. And what we do at each time step is we pass the decoder the previous word at the previous time step, and we have it try and predict the next word at the next time step. When we're trying to make a brand new prediction, we don't have the true English translation to pass to the neural network to have it take each previous word and pass it as input to the next time step of the decoder to try and predict the next word. Because if we had the true answer, then we wouldn't need to use our neural network to make a translation. So what happens in that case is, instead of taking the previous word that we know from the actual answer, we take our next prediction and we use that as the input to pass into the next decoder time step. Let me give you an example. We got an error. We actually got an error here, so we might have to fix something. Okay, we actually got an error here, and this is an interesting one because we expected our batch size to be 32 on our hidden size, but we actually got a batch size of 21. So the reason that is because our data loader splits up the entire data set into batches of 32, but if our total data set length is not divisible by 32, then one of the batches is going to have less than 32. So our final batch at the very end actually had a batch size of 21. So here is where instead of having our batch size hard-coded as 32, we want to get the length of the batch from the data loader. So what we're going to do instead is we're going to go, the batch size is just equal to the length of our tensor. And that way, when we initialize the hidden state, we get the correct batch size. So if we retrain this now, it will work. Okay, so I just want to illustrate what the issue is when we try to predict. Let's take this example sentence. So we have the English sentence, I am scared of big dogs, and we have this French sentence, j'ai peur de gros chiens. When we're trying to predict the entire English sentence and we don't know what the answer is, That means we don't have the previous word to pass into the decoder as input for it to try and predict the next word. So this is what we have right now. And in this scenario, we don't know what the prediction is. This could be a wrong prediction. It could be a correct prediction. We don't know. Let's say that this is the wrong prediction. So instead of predicting I, we predict he instead. In that case, at the next time step, it's still going to get past the correct input for the previous word. It's still going to get passed in the word I, because we're taking the inputs directly from the known target. When we don't have the actual answer, we have to pass in when we don't have the actual answer, what we do is we use our actual prediction and set that to become the input at the next time step. So in this case, our input at T1 would actually be the word he. And then we would be trying to predict the word am. In a prediction setting, we can't just use the previous word from the target, from the answer, because we don't actually have a target input. We have to use our next prediction that comes out of the decoder and use that as the input to our next time step. So what that looks like in code is we're going to have to change our forward and our forward step functions here. We're going to have two cases to consider. There's the case in training when we have an actual input, and there's the case in training when we don't have an input. So if input is not none, okay, when we have an input, and the other case is when we are given the input in training, and the other case is when we are not given input in inference. We have those two cases. In either case, we're still going to need to give our decoder an input here. Where first of all, because our input can be none, we're no longer going to get our batch size from the input. So let's just get our batch size from the encoder outputs, because that's a variable that's always going to be the same and it's always going to be given to us. Instead of taking the embedded, we're actually going to call this the decoder input. Okay, so this is going to be the decoder input. If we're given the input, then our initial decoder input at the first time step is just going to be equal to the embedded input, okay, at the first time step, right? Now here's where we would run into an issue. So if we didn't have an input, then our decoder input would just be the start of sentence token, right? We would just start it off as the start of sentence token. So in that case, we would create the empty array, and then it would have a batch size of 1, and then it would have torch.long, okay, and we would just fill it with the start of sentence. Okay, so this would be our input, but the problem is we would then have to pass this input through our embedding. So we would go self.embedding of this. So we're just going to switch things around a little bit. So instead of embedding the entire input at the beginning, what we can do is we can actually embed every single time step individually in the forward step. So we can just move this embedding part to the forward step instead, and nothing else is going to change if we do that. Embedded equals self.dropout of self.embedding of the input. Okay, and then instead of combining the input and the context, we just combine the embedded and the context. We no longer need to embed this. Okay, and then this is just going to be the input. And this is no longer going to have a third dimension coming from the embedding. So we're just going to have this, and we no longer need to embed this. let's just test this out and make sure that it works before we move on. Okay, so everything there seems to work. So this is good for now. So this is our initial decoder input. We're also going to need to get the decoder input at the next time step. And here we have two different cases, okay? So if the input is not none, I'm actually going to change the input to call it the target. Okay, so just to make things a little bit clearer. So if our target is not none, then our decoder input is just going to be the input or the target. Then our decoder input is just going to be the target at the next time step, which is going to be equal to I plus 1. Okay. And if our target is none, then what we're going to do is we're going to take our output and we're going to take our output predictions. We're going to find the word with the highest probability, and we're going to use that as our next decoder input. Because we're taking the softmax and we're doing this final output layer at the very end on the entire sequence, we actually want to move these two out and put them in the forward step as well. Okay, and this is not going to change anything either. So everything will still work if we do this. Okay, so let's just test that that is the case. Just want to make sure that we're not breaking anything. So let's run everything again. Okay, we did get an error here, so let's just see what did we do wrong. Oh, okay, this is just output now because we're doing it on each individual output. And we're getting an error here. Because we're transforming our outputs here in the forward step, that means that our output now is going to have it's not going to have a hidden size dimension anymore. It's going to have the output size dimension because it passes through the output to output layer. Okay, so that's the part that's going to change there. Okay, now let's try this again and make sure that it works. And we're not actually storing the output size anywhere, so let's add that as a parameter. Okay, and now it should work. So let's give that a try again. Okay, so looks like it's working. Perfect. All right, now let's go back to calculating the input at the next time step. Let's just make sure this works because in our example, we're actually passing in a target. So let's make sure that this works here. Okay, we also want to make sure that it works in the other case. We want to make sure that it works in the case where we don't give it a target. Okay, so where the target is none. So let's make sure that that also works. Okay, that works too. Okay, cool. So this is working. Now what we do is we take our output and then we just take the highest probability output. So we use our top k where k is equal to 1 and we do it over the final dimension. We do it over our output size dimension. Okay, and we can just squeeze out that last dimension. Okay, so if you recall, this is what our outputs look like, right? And if we take a single one of those outputs, we take the outputs at a single time step, okay? It's going to have this shape. And now if we call the top k function on that output, k equals 1. Sorry, We want to make sure we preserve the dimensionality here. So we slice the outputs at a single time step, which is replicating what we have when we get our output back here. And when we do that, we get a set of values and indices. And these are the indices that we get, okay? So it adds an extra dimension here. We don't need that extra dimension anymore. So we can squeeze out that last dimension, okay? And now we have the correct dimension. So now we have a single prediction for every single one of the sentences in the batch, okay? So that's why we do that, because when we call the top K function, it adds an extra dimension. So we want to just squeeze it out to make sure that we retain our original dimensionality. So this is going to be our decoder input. And then we just call this detach function, and all that does is it removes it from the gradient tracking. And so that way our next input, when we go to our next forward step, is just going to be the output from the previous time step is going to become our input into the decoder at the next time step. Now let's just make sure that works in both cases, and it seems to work. And let's try and train our neural network. Okay, everything seems to be working. And now we could also train the neural network without giving it the target, right? We still evaluate against the target at the very end, but we could still train our neural network and not give it the target and have it just use its next predicted output as the input to the next time step. So we could do it this way instead. And if we do that, you're going to see that it still works. Okay. Now we don't actually want to do that in practice, but we only want to do that when we're making a prediction. We don't want to do that in practice, but I just wanted to show you that that is actually going to work. Okay, so let's rerun everything from the beginning. Let's train it for a single epoch, and then let's write in the code to be able to perform a prediction with this neural network. Okay, so we finished training our model for the full 80 epochs, and we take a look at the loss, and the loss is almost zero. So almost definitely we are overfitting on this data set, but it's pretty impressive that our model is able to perfectly learn how to translate these French sentences into English sentences. Now let's see our model in work, and let's actually make some predictions. And let's make some predictions on some of our own inputs that the model has never seen. So, all right, let's do this here. Okay, let's not worry about the epoch loss. So we're just going to plot all of the batch losses. So let's get all the batch losses. So we're just going to plot the batch losses. And we're going to just do x at 2 for x in batch losses. Okay, and then the x-axis is the iterations, and the y-axis is the loss. So you can see how the loss is steadily decreasing here. Cool, so that looks good. Now let's clean this up, and we're gonna wanna rewrite our predict function. So our predict function is going to be fairly straightforward. We can just take the code for training here, and we can do this. And let's write this out step by step first. Just leave this as is. Okay, so French tensor, English tensor is equal to Yeah, so this is our French sentence. Then French tensor is equal to... Okay, so we can use our encode sentences function with a single sentence, and that should do exactly what we need it to do. So encode sentences. So we're going to do French sentence, and the language is equal to French. So this is our tensor. And then we're going to want to initialize the hidden state, and the batch size is going to be 1. Okay. And then we're going to want to get the output. We want to pass this through our encoder. So let's see here. Hidden.shape 1 by 1 by 128. 1 by 11. So it's tensor. Okay, let's try this and see what we get. Okay, and then we can go outputs and hidden is equal to, now we don't want to pass in any English tensor because we don't want to give our decoder the answer. We want it to predict the answer without any extra information. So we can pass in none as the target in our decoder, and then we can get the outputs. Okay, wonderful. Okay, and we have a batch size of 1, so we only care about the outputs at 0. Outputs in the first batch. Okay, and now we want to predict, so we want to use our top K to get the word with the highest probability for each of the time steps from our outputs. So we want to use this function here. And our outputs, okay, so we actually want to do this over the dimension of 1. And then we're going to remove the last dimension, or we can just index into the first dimension. Oh no, never mind. We're going to remove the last dimension. So we're going to go predictions is equal to the indices dot squeeze at dimension equals -1. So these are our predictions, and now we're just going to get the index to word x. I'm afraid of dogs. Okay. This is our sentence. So our English translation is equal to this. So we want to just get our English translation until we hit the end of the sentence. So we'll just do this. Okay, I am afraid of dogs. And we're going to do okay, so we were able to successfully translate the sentence "J'ai peur des gros chiens" into the sentence "I am afraid of dogs." So it didn't quite get exactly the correct translation. Our actual translation is I am scared of big dogs, but it got close. It got I am afraid of dogs. So I think that's still pretty good for a sentence that it has never seen. It is a little bit overfit. So if we had maybe stopped the training earlier, if we had created a validation set and stopped the training before it started to overfit too much, I think we probably would have been able to get the right answer. Nonetheless, I think this is pretty impressive, and this is pretty good performance. Let's put all this together into a function. So we'll go and now let's call predict on this French sentence. Wonderful. So now let's test this out on some of the French sentences in our training set and see how well our neural network is able to translate them into English. So let's give this a try. We're going to take a random sample, and then we're just going to pass it through our predict function, and we're going to print out the English sentence and the predicted translation. The French sentence "Je suis étonné pour ton audace," translated to "I am amazed at your audacity." And it looks like we've got all of these pretty much exactly correct. So probably what's happened here is our neural network has actually overfit and started to memorize the training set. So this isn't great, but showing us that our neural network is able to perfectly predict the training set is a very good sign. It would be interesting to run this neural network on the entire set of English and French sentences rather than the subset that we selected out. So that's where I want to leave off this video. If you watched all the way to the end, then I'm super grateful that you stuck with me through this video. It was a very long and somewhat complicated video. We covered a implementation of cross attention, and we built an encoder decoder neural network in order to translate French sentences into English sentences, and we were able to have it perfectly learn how to translate the set of French sentences that it has seen in the training set into English sentences. With a little bit of tweaking and by optimizing this neural network and not overfitting, you're actually able to use this to create a pretty powerful neural network for translating from French to English. I hope that this video was helpful to you. I hope that you learned something new. I hope that you were able to follow along. And if you enjoyed this video, then check out my channel for more videos just like this one, where I walk you through machine learning and how to create neural networks. And we do it all in code, where we write the code step by step together so that I can show you exactly how it's done. Once again, thanks for watching. Hope you enjoyed, and I will see you in the next video. Take care.